Earlier we have studied what is countable set in terms of a function f, which is 1 1 and on 2 from set of positive integers to set A. Then set A is said to be countable. Now we shall consider another part, that is the set which is not countable, which is uncountable. And we will see that the set R of real numbers is uncountable. Now we know the real numbers can be expressed in the form of decimal numbers, decimal representation of real number. For example, this is 2.4135, etc. This is a real number, or this is a decimal expansion of real number, or which can also be written in this form: 2 plus say 4 by 10 plus 1 by 10 square plus 3 by 10 cube plus 5 divided by 10 to the power 4 and plus so on. So decimal representation of real numbers that we shall consider here. And in general we say a real number can be written in the form b, it is integer part, and the decimal parts will may be denoted by a1, a2, a3 and so on, like this. So this is the representation of a real number in the form of decimal expression. And one more thing we may consider: 1/2. It can be written as 0.500, etc. Or it may have the expression as 0.4999 up to infinity. See, these are the two representations of 1 by 2. And 0.5, or here we if this is continued to infinity, means this becomes 0.5. So these are two representation, decimal representation of 1/2 are to be considered. So here this is 999. If it is continued, then it becomes 0.5. This type of expressions are there. And if you want unique expression, we avoid 9, repeated 9. So we shall consider now real numbers. And we will prove first result as a theorem. So this is a theorem 1.6. Earlier we have proved theorems related to function and countable sets. And the theorem, in this theorem we shall prove that the set closed interval 0 to 1, or this can be written as x belongs to R such that 0 is less than or equal to x is less than or equal to 1 is uncountable. This is our result. We want to prove this set is uncountable. Now we shall prove the result by indirect method, or that means we shall assume the contrary. Suppose this set is countable. Now the proof is: suppose zero, 1 were countable. So this means that every element of 0 to 1 interval is countable. We can count the elements, and therefore we can write this interval 0 to 1 as is equal to, say, x1, x2, x3 and so on, where every element of the interval 0 to 1 occurs among xi. Each element in this interval 0 to 1 occurs in this one of this may be equal to xi. And you see, this is the closed interval of real numbers x belongs to R means real number and x lies between 0 and 1. Endpoints are included in this interval. And we know that an integer, a number, not integer, a real number between 0 to 1 has the decimal expression having integral part as 0, say 0.2 may be like this, 0.5 or 0.41237, etc. This type of expression it will have, and at the most it will have 0.9 or 0.98, etc. So that means any real number in the interval 0 to 1 will have integer part at 0 and remaining is the decimal expression. And therefore each number x1, x2, x3 will be of this form. And we can write let x1 is equal to 0 point. Now the notation we shall use a11, a12, a13 and so on. So these may be 3, 4, 5, etc. any digit. And x2 is equal to 0.21, 22, 23 and so on. Likewise, xn is equal to 0.xn1, xn2, xn3 and in general it is xnn, and this may continue up to infinity and so on. So we assume like this. Now we will consider another formation of a decimal number representation or number between 0 to 1. Let, for that purpose, let b1 be a digit between 0 to 8. We will avoid 9 and we shall consider digits between 0 to 8 because we have seen 1/2 can be written as 0.4999 recurring up to infinity. So that is repeated. So we consider 0 to 8. B1 be a digit between 0 to 8 such that B1 is not equal to A11. B1 is different from this A11. Let B2 be a digit between 0 to 8 such that or we should consider between 0 to 8 this condition such that B2 is different from A2. B2 is different from second element in this representation and so on. Let Bn be a digit between 0 to 8 such that Bn is different from Ann. Now we shall form another number between 0 to 1. So for that number we consider like this. Let y is equal to 0 point b1, b2, b3, bm and so on. Then you see this y is different from any xi. So y is not equal to x1, x2 or any member of this representation or x1, x2 up to xn or up to infinity, because b1 is different from a11, b2 is different from a22, bn is different from xn, and therefore y is different from each of these xi. Then y is different is different from any xi, or you may say xn, n taking value from 1 to 3, etc. And since the reason is, since bn is not equal to an, bn is not equal to an, and also 0 is less than or equal to y is less than or equal to 1, because y has also the integer part as 0, 0 point b1 b2 etc. means this is a number between 0 and 1, and thus we have shown that y is a number between 0 and 1, but it is different from xi. Thus so y belongs to the interval 0 to 1, but y is not equal to xn, y is different. Y is different from any xi. Xn, n taking value 1, 2, 3, etc. So this is a contradiction to our assumption that every element of 0, 1 occurs among xi. This is a contradiction. This is a contradiction to our assumption. What we have assumed is every number between 0 to 1 occurs among xi. And this contradiction proves the result. Why this contradiction has arrived? Because we have assumed the interval 0 to 1 is countable. So this contradiction proves that the set is uncountable, and this completes the proof. So here we have first assumed it is countable. We have expressed the counting of it or elements of this as x1, x2, x3, etc. with this representation, and we have for another number y which is having this type of expression, and this y is between 0 and 1, but it is different from any of xn, and that means this y is not counted in this interval in this set. So therefore this set is uncountable. So this proves the result. Now next to this result we shall have a corollary, but the result is important and we write it as a corollary. And the corollary is the set R of all real numbers is uncountable. The corollary we shall prove is the set R of all real numbers is uncountable. Now this result is easy to prove using the theorem that we have proved now. Suppose R is countable. Suppose R were countable. Then the interval 0 to 1 is subset of R. Which is subset of R is also countable. We have a result as a subset of countable set is countable. So this is by theorem 1.5. Subset of countable set, though it is infinite, it is countable. But this is a contradiction to the result, above result. So this is a contradiction. Since the interval, closed interval 0 to 1 of real numbers is uncountable. And this contradiction proves that R is uncountable. Hence, so this proves R is uncountable. Or you see the interval 0 to 1, though it is having finite length of 1, it is uncountable, or it contains infinitely many real numbers. And we can't count the real numbers. So the set of R of real numbers is uncountable. Now we shall consider some examples from the exercise. The exercise in the book is 1.6. So the first example is, if f is a function from a to b and the range of f is uncountable, then prove that the domain of f is uncountable. See, if f from a to b means f is a function from a to b, the range of f is uncountable, then prove the domain of f is also uncountable. Now we shall prove the result by taking the definition of range of a function and domain of a function. Now here it is clear that domain of function is a. Function is from a to b, therefore the domain of the function is a. And we are asked to prove domain is uncountable, the range is uncountable. We shall prove the result by again indirect method. Suppose the domain of f, which is a, is countable. Suppose the domain of f is countable. That is, the set A is countable. And if it is countable, we can express it as, therefore we can write A is equal to, the elements are counted, we can write the elements as A1, A2, A3 and so on. Now the range of F it is actually equal to F of A, F image of the domain, or this will be equal to F of A1, F of A2, F of A3 and so on. By definition of function, every element in the domain has the image. So that set of images is range of F. And see, because A is countable, F of A is countable. So therefore, and here we will avoid the repetitions in the range. Since A is countable. That is, range of A is countable. Range of F is countable. And this is a contradiction because what is given? Range of F is uncountable. And why this contradiction arrived? Because our assumption is wrong. What is our? We have assumed the domain of F is countable, and thus the domain of F must not be countable, that is uncountable. And hence, the domain of F is uncountable. So this proves the result. Now the second example which we consider is if B is a countable subset of an uncountable set A, then A minus B is uncountable. So this is the second result. Now how to prove this? So what is given here is B is countable and A is uncountable and B is subset of A. So then we shall have to prove A minus B is uncountable. We shall consider a solution for this. Suppose this is the set A. And because A it is uncountable and B is subset of A, so B will be here in the figure. A is uncountable, B is countable. What is asked? A minus B is uncountable. So which is the set A minus B? That part of A which is not in B, or those elements of A which are not in B, and that means this ring shaped region will be of A minus B. So this we have to prove that A minus B is uncountable. Now we suppose again the contrary, that suppose A minus B is countable. Suppose what is given? B is countable. And now you see A is equal to the set A is union of these two sets, A minus B union B. Then A becomes union of two countable sets. A minus B is countable, B is countable. So A is union of two countable sets, and we have the result are here. Union of countable set is countable. So thus A is union of two countable sets. And therefore A is countable. Earlier here we have proved, and this is a contradiction because A is uncountable. And hence this contradiction proves A minus B is uncountable. Now you see one more result. Third example is the set of all irrational numbers is uncountable. The set of all irrational numbers is uncountable. This you can prove using the result, earlier result, say solution for this. Now we have the information about real numbers and rational numbers. So what about the set of real numbers? Set of real numbers is union of rational number and irrational number. And among that, rationals, we have proved the result earlier. Set of all rational numbers is countable. So this information we shall use. Let R be the set of all real numbers. Q be the set of all rational numbers. And Q dash be the set of all irrational numbers. And now R is equal to rationals union irrationals gives the set of real numbers. What we have to prove is the set of rational numbers means Q dash. Q dash is uncountable, that we have to prove. So we write the information here as we know that R is uncountable, or earlier to that we will consider Q is countable. We write about Q. Q is countable. Suppose Q dash is countable. Actually, we have proved Q dash is uncountable. We suppose the contrary result, Q dash is countable. Then R becomes the union of two countable sets. R is the union of two countable sets, and therefore R is countable because union of two countable sets is countable, and thus therefore R is countable. but this is a contradiction. R is uncountable. And hence the set, this assumption is wrong. Q dash must be uncountable. Hence the set of irrational numbers Q dash is uncountable. Or all irrational numbers is uncountable. So this is about uncountable sets, and we have shown that R is uncountable. The closed interval 0 to 1 is uncountable, and according to that we can consider any closed interval of real numbers will be uncountable. Closed or open interval maybe. It's not only 0 to 1, but the interval 1 to 2, or the interval say minus 4 to minus 3, etc., or minus 5, whatever you may consider, are all uncountable. So this is about uncountable sets. So okay, thank you.